Okay, so we've looked at series in circuits, and now it's time to look at parallel in circuits. So we're going to start out with notes that look a little similar, but what we're going to add is going to be different. All right, so first of all, what does it mean to be in parallel? It means that the components there we go. Are connected at junctions by wires. Now that last piece is important. We never put components in a junction. So that means that if we look at, for example, this right here, that's a junction. It's where multiple things are coming together. We would never want to draw a capacitor or a resistor or a switch in that space. All right. The next piece is, remember when we did series, we said current stays constant through the circuit. Well, now when we're talking about parallel, it's the potential difference that stays constant. Through the circuit. So when we go to do this math, it'll have a little bit different meaning to it, and we'll see. We'll play that out. Okay, so here's a set of resistors. Remember, resistors are our squiggly lines, and I have 1, 2, 3 resistors, and I'm going to run some voltage through there. And if I want to find that equivalent resistor, this is going to look familiar, but it's going to be opposite what we think about based on what we did before. This looks just like the capacitors did, and it works just like the capacitors did when they were in series. So again, if I wanted to keep going, if I had 4 or 5 or 6 resistors, I could. So the procedure here, just in case we're watching these without the other guy around, without our other videos around, is we're going to add the fraction, and then we're going to reciprocate, or flip it over. And what this means is that when we're in parallel, resistance shrinks. The amount of resistance I can expect is less than just adding up the pieces. All right, so let's compare that to capacitance. And I have capacitor 1 and capacitor 2 and capacitor 3. If I want to find my equivalent capacitance, I'm going to take capacitance 1, capacitance 2, capacitance 3, and get my total. Just going to add them up. So going back to what we know from previous videos, that means capacitance grows or increases when it's in parallel. So these are opposite to the video we just watched. Okay. So I'm going to scroll down here just a little bit and give a quick review of your first video when we're connecting meters, electric meters, multimeters, connecting our multimeter. Normally I would have you guys do this with me, and we'd already have practiced with actual multimeters. So there's some things that were a little bit missing this COVIDcation. And if I ever use these videos again, now you'll know we're recording them in the COVID-cation. When we want to measure resistance, we're looking at this symbol added into our circuit picture, and we're going to insert them in parallel with our component that we want to measure, and we want to make sure that the power is off. If we're measuring voltage, we want to usually, in a physics class, have this guy because we're doing direct current. And we want to still be in parallel. We want to wire it in so the meter looks like one of the components in a parallel system. And if we're looking at current, we're going to have that, an amp in a circle, written into our diagram. And we want to make sure that these guys are in series. And the other little note there is that you need to move the red lead. So for the first two, if I had a resistor that I wanted to measure, I would write them in like this. And that would work for ohms and for volts. But for the current, if I had something that I wanted to measure, I would wire it in after the fact, and I would put in a little A for amps, because that's what I'm measuring. Ohms, volts, and amps. All right, usually you draw that A inside the circle. I didn't leave myself enough space. So my question is, with that in mind, which of these circuits has the multimeters correctly attached? It should probably say multimeters because it shows two of them. Take a moment, push pause on the video, analyze those, and only one of them is correctly installed. So have a look and tell me which one. Okay, I'm about to start talking, so if you haven't figured it out already, please push pause and take some time and analyze. It doesn't matter if I push pause. When I hit play again, I'm going to be right back and there's no time passed. So you need to hit the pause button. All right, so remember we said anything that looks like this, that can be our ohms and our volts, and anything that's wired separately after the fact in series needs to be our amps. Okay, so we're looking for, since we only have volts and amps here, we weren't interested in ohms in this particular problem. This guy's got amps drawn in parallel, so that's not it. This guy has both amps and volts drawn in series, and volts can't be in series. Volts need to be in parallel, so that's not it. I'm going to keep going clockwise here. This one has the volts drawn in series with our component. When I say in parallel or in series, I'm talking about with that resistor. And it's got our amps drawn in parallel, so that one is completely backwards. So hopefully this one's going to work out. If I'm running around, here's my amp meter wired right in series, so in the same line, and connected outwardly in parallel, there is my voltmeter. So that one checks out with the system that we have. C is the right answer to the question. Okay, so we're only 10 minutes in on this video, so I think I'm going to jump ahead and just do the very first problem. The reason is the last problem's kind of long. So if we get this one out of the way, I should still have time to do the other 3 in one video for you guys. So it says, what is the current provided by the battery below with 58, 70, and 45 ohm resistors in parallel? So the reason I spelled that out in the question is because I drew the picture really sloppy. So we know that when we're doing resistors in parallel, that the equivalent is 1 over R1 plus 1 over R2 plus 1 over R3 will give me 1 over my equivalent. Okay, you should hit pause now. That's a pretty good clue to start with. And do the math yourself and make sure that you can work it out. So hopefully you've tried this and you've hit pause. And here's what I have. I have 1 over 58, which I would do in my calculator, all in one step. 1 over 70 and 1 over 42. So use of parentheses is a good idea. And what I get out of my calculator is 0.055. So 0.055 is 1 over Req. So if I want to get my equivalent resistance, I need to reciprocate that. So if I want to get equivalent resistance all by itself, I'm going to do 1 over 0.055, and I'm going to get 18.07 ohms. Now, does that make sense? Well, we said up above, if you put them in parallel, you're going to get less out than you put in. And 18 is a lot smaller than even 42. So just to add another piece like I did on the other video, something that can help us, we've got that. What is the current running through this? Now that we've got voltage and resistance, what would that current look like? Well, V equals IR is our starting point. So I equals, gosh darn, 1 second please, equals V divided by R. Okay, so then that is 12 divided by 18.07 that we calculated. And our current running through the system is 0.67 amps or 670 milliamps. So I didn't ask you to solve that, but if you were looking at this picture and I said, hey, what's the current flowing through those wires? You'd need to actually go back and do the resistance equivalent first, and then you could answer the question. All right, that's 13 minutes. That's a good place to stop this video. We're going to have one left, and here's hoping YouTube works for us this time.